All right, we're coming to the end of Chapter 4. Chapter 4 is on applications of differentiation. In this video, we're going to go through Section 4.9, which is on antiderivatives. Now, some of you might be asking yourself, well, an antiderivative, isn't that an integral? And my answer to that is, so the way this course, this playlist is set up, is that we've been going through the calculus textbook, James Stewart's calculus textbook, in sequence from the start. We skipped Chapter 1. This was like pre-calculus, but the official calculus material started in Chapter 2, limits and derivatives, and we've been going through section by section. So the idea is we want to learn the calculus, but then also follow the story of the calculus. So how the subject develops, how everything builds. Okay, and so Chapter 2, we do limits and derivatives. Chapter 3, differentiation rules, and then Chapter 4, applications of differentiation. And when we're done with Chapter 4, that's the end of what people call Calculus 1, differential calculus. In Chapter 5, we start Calculus 2, or integral calculus. But all throughout Calculus 1, Chapters 2, 3, and 4, we've never heard the term integral. And we're not going to hear it in this video either, in Section 4.9 either. We won't hear it until Chapter 5. Okay, so it's important for you to understand this. So keep this in mind. It's particularly important if you really want to grasp the fundamental theorem of calculus. All right, in the context of going through this textbook in sequence, in all of Calculus 1, we have never heard the term integral before. And we're not going to hear it in all of Calculus 1. The last thing we're going to do in Calculus 1, in this video, in Section 4.9, is we're going to think about the idea of, so we know how, if we have a function, what we've learned, if we want to we can take the derivative of this function, and we'll call that capital F of x. That's the derivative of f of x. We know how to do that. But we want to think about the idea of, well, what if we start with a function at capital F of x, and we want to figure out what the function is whose derivative is the capital F of x. We want to go in reverse. But note, though, this is the first time we've ever thought about this idea. Well, technically, we did touch on it a little bit in Section 3.8. The textbook does, but I skipped that section. We go into detail in exponential growth and decay and differential equations, so we skipped that section. And so in this course, this video, Section 4.9, is the first time we've ever thought about the idea of what if we want to go in the opposite direction of differentiation. We're given a function, and we're saying that function is the derivative of some function, and we want to find that original function. Okay? Now, if imagine you were inventing calculus. So you're Isaac Newton, and you just invented differential calculus, and you're coming to the end of differential calculus, and now you're thinking about this idea of going in reverse. You want to name this process something. What would be a good name for this process? Well, here's a really good name. You could call it an antiderivative. There you go. Again, we don't have no idea what integral is. We've never heard that term. We're going to call this process antidifferentiation. We have a function, capital F of x, and we want to find its antiderivative. Okay? So let's go through Section 4.9 and think about this idea of antidifferentiation. All right, a physicist who knows the velocity of a particle might wish to know its position at a given time. An engineer who can measure the variable rate at which water is leaking from a tank wants to know the amount leaked over a certain time period. A biologist who knows the rate at which a bacteria population is increasing might want to deduce what the size of the population will be at some future time. In each case, the problem is to find a function f whose derivative is a known function, so a function capital F whose derivative is a known function lowercase f. If such a function uppercase f exists, it is called an antiderivative of lowercase f. All right, so what are they saying here? They're giving examples of these situations in science and engineering where you know a function and that function has an obvious, what we're calling an antiderivative. So a physicist knows the velocity of a particle as a function of time. A physicist has this function, not just like one moment in time, but like this whole function, right? A full function that's continuous over a range. The velocity is a function of time of a particle. but the physicist wants to know the position of that particle. And the idea is, you know, that the position function of that particle, the position as a function of time, is going to be what we're calling the antiderivative of that velocity function, right? Isn't that an interesting idea that we haven't really thought about yet up to this point in calculus? A biologist who knows the rate at which a bacteria population is increasing might want to deduce what the size of the population will be at some future time. So you know the rate of change of the population of bacteria. Somehow you know that. But it's not just at one moment in time. You have that whole function, right? It's like the velocity function. You don't just have the velocity at one moment in time. You have the whole velocity function. From time t is 0 to 3 minutes, you know the velocity at, you could just plug in any time, as long as it's between 0 and 180 seconds, and you can get the velocity, the accurate velocity. So you have the velocity function. So you're saying, okay, well, can we solve for the function whose derivative is the velocity function, right? You know the rate of change of the bacteria population with respect to time. You have the whole function. But can we solve for the function whose derivative is this rate of change of the bacteria population function? And if you think about it, that function would be the bacteria population at any moment in time. Not the rate of change of it, but the actual bacteria population, okay? So in each case, the problem is to find a function, capital F, whose derivative is a known function, lowercase f. If such a function, capital F, exists, it is called an antiderivative of f. That's what we're calling it. Get integral out of your head. We don't know what integral means. If we called it an integral, someone would say, what the hell does that mean? What does integral mean? Is that Greek for something? We have no reason to call it integral. Right now, we're calling it antiderivative. Okay, so definition. A function, capital F, is called an antiderivative of lowercase f on an interval I. So, you know, it doesn't have to be, it can be over a certain interval, if depending on the circumstance, right? So you might have, you know, it goes from 0 to 500, you can find an antiderivative, but you're ignoring everything else outside of that range. Or maybe it's for all real numbers you're finding an antiderivative. It just depends. Okay, but the capital F is an antiderivative of lowercase f on an interval I if what? If f prime of x is equal to f of x, lowercase f of x, for all x in I. Okay, so wait, I'm a little confused by the notation here. I thought they were saying that we've got a function f of x and we take its derivative and we get capital F of x. Maybe that's not what they're saying. Yeah, so it looks like they're saying the opposite. So it's, all right. And just note, this is just notation. So it's saying we have a function f, capital F of x, and you take its derivative and you get lowercase f of x. And we're trying to find capital F of x. So in all of these situations here, the velocity function is lowercase f of x. The rate of change of the bacteria population is lowercase f of x. And we're trying to find the position function, capital F of x. The bacteria population is a function of time, capital F of x. So capital F of x is the antiderivative, okay? So the capital F of x is the antiderivative. The lowercase f of x is the function that we know. For instance, let f of x is equal to x squared. All right, so let's find an antiderivative of f of x is equal to x squared. What is capital F of x in this situation? Well, all right. We can think about this in the sense of the power rule. So if we're going to take the derivative of something and have x to the power of 2, well, we know from the power rule that if you take the derivative of, let's say, x cubed, you get the derivative of x cubed is 3x squared. So if you have something x cubed, then you're going to get something x squared. So we can start with x cubed. Okay, so the derivative with respect to x of x cubed is 3x squared. So that's a start. But it's 3x squared, not 1x squared. Okay, so if we want to get 1x squared, well, we know from the power rule that you bring the 3 down, and so you multiply by the coefficient, the 3 by the coefficient. So if we want to multiply 3 by something and get 1, then we can put 1/3 here. All right, so now, there we go. So if we take this derivative with respect to x of 1/3 x cubed, that gives us x squared. There we go. Perfect. So there you go. There's f of x, or capital F of x. The idea is capital F prime of x is equal to f lowercase f of x, and that's the case. Okay, but there's something to consider here. What if we added 100 to this? Well, in that case, capital F prime of x is also equal to x squared, because the derivative of 100 with respect to x is 0. So there's multiple functions whose derivative equals the lowercase f of x. And based on what we did here, we could potentially say that, well, let's just make this any arbitrary constant. And so in which case, if this is just a constant, then capital F prime of x is equal to 1x squared. Okay, but a question that comes up then is that, is this the most general form for the antiderivative of this of x squared? Like, does this represent all possible functions whose derivative results in 1 times x squared? And the answer to that is yes, it is. And the explanation they give for this, it says, to answer this question, recall that in section 4.2, we use the mean value theorem to prove that if two functions have identical derivatives on an interval, then they must differ by a constant, right? That's something we talked about in section 4.2. If you have two functions, they could be the same, but let's just say they're different, and you take their derivative, and their derivatives are the same, either over all real numbers or just over a certain interval. Then if you subtract those two functions, not the derivatives, those two functions, it's going to be a constant. If it's the same function, then you subtract them, it's going to be 0. But if they're different functions, but they have the same derivative, if you subtract those different functions, you're going to get a constant value every time, no matter what. That's what was proved in section 4.2. Okay, and so with that idea, I'm not going to give you an official math proof here, but you can reason that, knowing that that's the case, that if two functions have the same derivative, then those functions must differ by a constant. Then the most general form of the antiderivative of any function is given by, you find the antiderivative with respect to x and then just add plus c at the very end, plus arbitrary constant at the very end, and that's the most general form. And the reason they give here is, so, okay, you've got the antiderivative f of x and g of x, two different functions, but their derivatives result in the same function. Okay, so we proved in section 4.2 that means that capital G of x minus capital F of x, not the derivative of the original functions, is equal to a constant. Okay, so we can write then, if you add f of x to both sides, capital G of x is equal to f of x plus c. And what this is saying is that, starting with a function whose derivative is lowercase f of x, you can get to any other function whose derivative is that same f of x by just adding a constant at the end. And so with that, that's proof that if you're finding an antiderivative, then once you find the antiderivative, to get the most general form, just add an arbitrary constant at the end. Now, this still might be a little confusing to you, so let me clarify something here. You're going to be given, okay, so you're going to start with an f of x, okay? You're going to start with an f of x. You want to find an antiderivative of f of x. This f of x here, it could be just some expression of x, or maybe it has a constant in it, right? X squared plus 100, that's a function of x, right? So this f of x could be anything. You see what I'm saying? Like, this 100 is included in the f of x. X squared plus 100 is f of x. So you start with any function of x, or of a single variable. You start with that, okay? The first thing you're going to do is, so you're going to find its antiderivative. You're going to find capital F of x. What am I saying there? You're going to find, and this is a little confusing, capital F of x is going to be anything. It's going to have x terms. All right, this is confusing because I just said that lowercase f of x could have terms that don't have an x in it, but the capital F of x is going to be only terms that have x's in them, right? So if this was x squared plus 100, then the capital F of x is 1/3 x cubed plus 100x. The derivative of this is x squared plus 100, right? These terms have x's in them. That's like the f of x. Like I know this is I know this is confusing because I'm saying that lowercase f of x can have a term that doesn't have an x in it. But that makes sense because we know just general functions like that we learn in algebra can have terms that can have constant terms. But this capital F of x so this lowercase f of x isn't associated with any derivative definitions. This is just straight from algebra, right? You can have a function of x can be anything with constants in it, whatever. But this capital F of x is associated with this antiderivative definition that we're talking about right now. So in this context, this capital F of x only has x terms, only has terms that variable terms in it. This capital F of x has no constants in it. We're strictly talking about the terms that have x's gathered together to where when you take the derivative of f of x, you get the original function back. You see, once you've got this capital F of x, to get the most general form, you add a c at the end, at the very end of it. So all this is grouped together, no matter how complex it is, and at the back end, you add a c. And then that's the most general form because, yeah, f prime of x is x squared plus 100, and then derivative of c with respect to x is 0, so you get f of x. That's it. That's the idea, okay? So it gives an example here, just for f of x is equal to x squared, the antiderivative is x cubed over 3 plus a constant. So it's just the same curve with the same slopes. The slopes are the same everywhere, but the curves are shifted. So all these curves have the same derivative. Okay, now the rest of this section, it gives examples of finding antiderivatives. So just like we did here for x squared, we kind of went in reverse and used we reversed the power rule. But I don't want to go through all this. In fact, I don't even want to work any example problems for this section, because yes, integration, the term integral, to take an integral, you do have to find an antiderivative of a function. So, you know, the integral of f of x dx, you need to find the antiderivative of f of x to get this integral. And so with that, we've got 5 chapters of integration coming up. We're going to go into so much detail and depth on finding antiderivatives. So to me, it's a waste of energy to start looking at this in detail now. Okay, and that's all they're doing here. So okay, what's the antiderivative of sine of x? Well, what function when you take the derivative gives sine of x? Well, cosine of x gives minus sine of x. So maybe minus cosine of x would give sine of x. But then so minus, if f of x is equal to sine of x, then the f of x is equal to minus cosine of x. So the derivative of minus cosine of x gives positive sine of x. But then this is the capital F of x. You got to add a c at the end. So the antiderivative is minus cosine of x plus c. That's what we're going to do. They do this in the rest of the section, but there's no need. We're going to be going into so much depth on this process for integration. So again, there's no point even going through these example problems in the section and working example problems at the end of the section. But just note, though, again, we don't know. Just imagine we don't know what integration means. We've never heard the term integral. We were just talking about antiderivative, the idea of an antiderivative at the moment. Okay, so here's the general antiderivative. If you're doing like the reverse power rule, they give other antiderivative rules here. I don't want to get into all this. Okay, it says in applications of calculus, it is very common to have a situation, as in example 2, where it is required to find a function given knowledge about its derivatives. An equation that involves the derivatives of a function is called a differential equation. These will be studied in some detail in Chapter 9, but for the present, we can solve some elementary differential equations. The general solution of a differential equation involves an arbitrary constant. And then, once you have boundary conditions, you can solve for that constant. Boundary conditions are like okay, at time t is equal to 0, what's the starting position? Then you can solve for the constant. You know, they're bringing this up here because for differential equations, you need to you're finding antiderivatives. What a differential equation is, so if you're modeling something, you know, you're doing any kind of mathematical model on some phenomenon, well, you can introduce variables, meaning so the amount of this something is equal to B, the whatever is equal to this, like variables that represent the quantity of something. But you could also introduce variables in the sense of that represent the rate of change of a quantity. So like the drag force on a vehicle from the wind, okay? The drag force on a vehicle from the wind, if you think about it, that's going to be a function of the velocity of the vehicle to some degree, right? That'll be a function of the velocity of the vehicle. And so you might come up with a differential equation that's representing the drag force on the vehicle as a function of the velocity. Well, what is the velocity? That's the change in position with respect to time. So maybe you want that would be a differential equation that it involves the derivative of a function. So you're trying to solve for the position. So you got this equation that has the derivative of a certain function, and you're trying to solve for that original function. And as you can imagine, that involves doing antiderivatives. Okay, but that's differential equations. That's a topic for another day. Okay, so here's just more antiderivative examples. Rectilinear motion. Yeah, so this is the classic example that, so like if you have the position of something with respect to time, you take its derivative, you get the velocity. You take the derivative of the velocity, you get the acceleration. That's rectilinear motion. So you can solve for, you know, the positions of something and its velocity and acceleration. You're going back and forth between differentiation and then anti-differentiation. That's called integration, but right now we're just calling it anti-differentiation, right? So you can see with S of t, V of t, A of t, this is the position of something with respect to time, derivative, but then antiderivative, right? So this is a classic example of that they'll use to illustrate, you know, differentiation and anti-differentiation. All right. So yeah, that's it. That's the idea of anti-differentiation and antiderivative. And again, so I'm not going to do any example problem videos on this section. To do an integral, you have to find an antiderivative, and we're going to go into a lot of depth on all the techniques for finding antiderivatives as we go through integration in Calculus 2.